Today I will be presenting our SOK work on usable privacy, the lack of overlap between privacy-aware sensing and usable privacy research. This work was done while I was at the University of Michigan with my colleagues Pardis Imaminaini and Alanson Sample. Ubiquitous computing is everywhere. 30 years ago, Mark Weiser described a future where computing devices blend into the background and only become present when we need them. Since then, the descendants of these clunky devices have woven themselves into the fabric of our daily lives, into what we now call IoT. But now with the level of access they have to our lives, there are profound privacy implications. And Weiser recognized this privacy challenge from the start, seeing that having hundreds of computers in every room with sensing capabilities could lead to significant privacy issues. He follows up with a potential solution, stating that cryptographic techniques can secure messages from one computer to the next to safeguard that information. However, we know from privacy incidents that encryption alone may not be enough to safeguard privacy. Ubiquitous computing's disappearing act has led to a privacy side effect, and it's partly due to changes in how these systems are built. Before it was your computer, your data, and your hard drive, and access was limited. And users still largely believe that because they own the device, they also own the data. But many incidents show that this is not the case. So why is privacy for ubiquitous computing such a hard problem? First, not every device uses the same set of sensors, so what invokes privacy concerns and how to address them will differ for each device. Second, different applications have different information needs. Solutions that will improve user privacy for one scenario may completely break an application in another. Third, users have different privacy needs, especially given the context of what their application needs are. For example, elderly populations may relax their privacy needs for health monitoring, such as fall detection. Other populations may not see the value and maintain higher privacy needs. These factors make it virtually impossible to have a one-size-fits-all solution, and this results in a tension between the growth of sensing devices and individually addressing their privacy issues. And one last thing is that only recently have laws started to set standards for privacy and data collection. And as this fantastic paper from last year's PETS states right in the title, those things are written by lawyers and programmers are reading that. So even though we're getting standards now, lawyers don't have the technical background to write them necessarily, and they're too vague often for engineers to implement. The ubiquitous sensing community has been aware of these privacy challenges, and I frame my work on Mark Langheinrich's Privacy by Design for Ubiquitous Systems, which outlines 6 principles rooted in user-driven privacy needs to help build trust and protect users. I summarize these principles as follows. Notice, where a system should notify the user when collecting data. Choice and consent, where a system should allow users to choose and consent to data collection. Anonymity and pseudonymity, where a system should be able to collect data in a way that cannot be traced back to the user. Proximity and locality, where a system should confine their sensing ability to within a user-specified range or locations. Adequate security, where a system should employ measures to secure and protect sensitive information. And access and resource, where a system should only collect data sufficient for a well-defined purpose which a user can audit. To find relevant works for the SOK, we identified 12 venues spanning 4 research communities: human-computer interaction, mobile systems, security and privacy, and usability and privacy. We grouped these venues into these communities based on their SIG relationships, overlap in program committees, and topics in their call for papers. The title and abstracts of works from these venues were collected between 2018 and 2023, resulting in 10,122 works. These titles and abstracts were converted to embeddings with the OpenAI ADA 002 model. We developed an interactive sorting model, but for the sake of time, I will refer to the paper for further details. This interactive sorting model was seeded with a small set of labeled works for initial training. Moving forward, we start with an initial set of predictions. We then label the works at the top of the list with a value from 1 to 5. 1 denotes a work that is related to both privacy and sensing. 2 is related to either privacy or sensing and a related field. 3 is related to either privacy or sensing. 4 is related to only a related field, and 5 is completely unrelated. As part of this interactive sorting tool, a random jump feature was included to avoid getting stuck in a neighborhood of related works and allowed us to sample different areas. This process was conducted until qualitative saturation, resulting in 600 papers reviewed through this process, of which 117 were labeled as a 1, denoting a high likelihood of being included in our codebook. We then evaluated these 117 works through our inclusion-exclusion criteria. To summarize, our inclusion criteria were that works must have incorporated at least one of the Langheinrich Privacy by Design principles. Of the 117 candidates, only 3 were excluded as they did not directly engage in mitigations for sensors or privacy, in addition to not incorporating a privacy by design principle. This resulted in 114 total works included in the codebook. As part of our systemization work, we defined additional characteristics to code the works by. We characterize their works based on their primary identity. Where does the work self-identify as its primary contribution? As a privacy-aware sensing contribution or a usable privacy contribution? We then characterize based on their privacy factor what kind of mitigation is being proposed. This included authentication, which uses user identity to define system behavior, granularity, which reduces the resolution or range of the system's sensing or data collection; purpose, which the system uses purpose-built sensors to restrict its ability to collect certain types of privacy-invasive data; sanitization, where a system actively removes or prevents the collection of privacy-invasive data; and control, where the system presents user-accessible actions to determine sensor behavior. We also categorize the work's privacy mindset, which represents how the work contextualizes its privacy mitigation. This included the all-or-nothing mindset, which presents a binary perspective on privacy and proposes an absolute privacy mitigation; better than nothing, which presents a gradient perspective on privacy and proposes a mitigation that has known and well-scoped limitations; security is privacy defensive, which presents a defensive security measure like system hardening and encryption as a proposed privacy mitigation; and security is privacy offensive, which presents offensive security measures like sensor jamming and attacking privacy-invasive systems. And finally, awareness, which presents user understanding and awareness of system behavior and data collection as a user-driven privacy mitigation. We also characterize the work's evaluation approaches. In essence, how did the work evaluate for success? This included technical, where the work demonstrated a quantifiable increase in privacy; user, where the work was evaluated for user factors such as acceptance, usability, or comfort; feasibility, where the work evaluated the feasibility of the proposed mitigation, such as with a prototype, research artifact, or operational system; and system, where the work evaluated a system incorporating the mitigation and its impact on performance and privacy-preserving ability, rather than solely the mitigation in a vacuum. Based on these characterizations, we identified 4 key themes in the existing literature. First, control and awareness form the cornerstone of usable privacy. In usable privacy work, privacy mitigations are often framed around giving users both control and awareness. That is, users are not only notified when sensing occurs, but are also offered tangible ways to intervene, such as muting, disabling, or modifying sensing behavior. This reflects a strong emphasis on user agency. In contrast, privacy-aware sensing works tend to avoid the control factor, favoring passive protections that minimize user burden. This contrast points to a central tension. How much should privacy protections depend on user engagement? At what point does empowering the user become offloading responsibility? Second, we observed a thematic divide between what we call all or nothing and better than nothing approaches. The underlying friction here is between formal guarantees and pragmatic usability, which is heavily influenced by the importance of user experience. Third, we found that many privacy-aware sensing contributions often make unvalidated assumptions about user needs. These works often demonstrate technical merit, such as through effective data sanitization or system-level defenses, but do not engage with users to assess whether the proposed mitigation is actually acceptable or useful in practice. There's typically an implicit assumption that because a mitigation addresses a known privacy threat, it will be well received. But in the absence of user evaluation, that assumption remains speculative. Fourth, we observe that user-driven privacy mitigations often lack feasibility or system-level validations. Many usable privacy works are grounded in rich qualitative insight, often identifying meaningful user needs and translating them into design recommendations. However, these works frequently stop short of evaluating whether their proposed mitigations are implementable in real systems. These themes also appear in our quantitative findings and have clear consequences for how research is conducted. If we categorize works by their primary contribution, either usable privacy or privacy-aware sensing, we see a sharp divide in how each group evaluates their work. Almost all usable privacy papers evaluate their contributions with users, but they rarely include technical or systems-level evaluations. In contrast, privacy-aware sensing papers almost always perform technical and feasibility evaluations, and most also include a systems evaluation, but they infrequently assess whether users actually accept or understand the mitigation. We also see differences in the privacy values each community encodes in their designs. Usable privacy works tend to focus on notice and choice and consent. In other words, making the sensing visible and giving users some control. Privacy-aware sensing works almost invert that emphasis. They rarely implement notice or choice, and instead prioritize anonymity and security, principles that aim to protect privacy passively without requiring user engagement. This divide isn't just visible in the evaluation methods or privacy principles, it also appears when we look directly at the embeddings of these works. To generate this figure, I created a T-SNE projection of the vector representations of all 10,000 plus collected papers, color-coded by research community. The usable privacy works we included in the codebook are marked as orange diamonds. The privacy-aware sensing works are shown as gray crosses. Unfortunately, there's very little overlap between the two. Even though both groups work on privacy and sensing systems, they tend to speak different languages, conceptually, methodologically, and even literally in terms of terminology. But if we look near the center of the figure, we start to see something encouraging. A small but emerging cluster of works that sit at the intersection of all 4 communities. These works begin to combine usable privacy principles with sensing, systems, and security approaches. However, if we zoom in, We still see that this intersection is sparsely populated. There's no critical mass yet, so the question becomes, what's holding back the cross-pollination that this field clearly needs? One of the key challenges here is that the communities we need to come together don't actually overlap much in practice. And the statistics reflect this gap as well. We calculated the Bhattacharya coefficients, or BC values, for each pair of communities. These values range from 0 to 1, where 1 means two communities are perfectly overlapping in their research space, and 0 means they share nothing in common. As you might expect, there are some strong overlaps, but the combinations that matter most for cross-disciplinary UPAS works have some of the lowest overlap values in the whole matrix. These aren't just numbers. They help quantify the structural barriers to interdisciplinary collaboration. Even when researchers care about the same broad problem, they often don't find each other's work, publish in the same venues, or speak in the same terms. So the fragmentation we saw in the embeddings isn't incidental, it's systemic. And addressing this will require more than just technical innovation. It will take deliberate community-level efforts to connect across these divides. So where do we go from here? First recommendation is to increase the diversity of privacy principles that researchers draw upon. Usable privacy works can engage more directly with systems constraints and embed privacy deeper into hardware and sensing architectures. Privacy-aware sensing work, in turn, could explore how to incorporate notice consent and transparency, but as first-class system properties. Second, we recommend evaluating privacy mitigations end-to-end. This means going beyond a single dimension of success. Strong privacy guarantees don't mean much if users don't trust the system, or if the system can't be built. Likewise, elegant interface concepts won't matter if they assume unrealistic capabilities or ignore security threats. We need work that addresses feasibility, usability, and effectiveness together. To conclude, we used an embedding-based sorting approach to sift through over 10,000 collected works, narrowing them down to 117 highly relevant candidates. Out of those, 114 met our inclusion criteria and were fully analyzed. Through qualitative and quantitative analyses of those 114 works, we identified 4 key themes that highlight methodological and conceptual divides in the field. We also used direct embedding analysis to visualize this gap, showing how little overlap there is between core privacy-aware sensing and usable privacy contributions. Our central takeaway is that greater cross-pollination between these communities is not just possible, it's necessary. Bringing together usability, technical feasibility, and privacy protections will lead to more robust and adoptable sensing systems. Thank you for coming to this talk, and I'll open for questions.